Hi, everybody. Welcome back to Introduction to Physics, day 11. We yesterday talked about kind of our introduction to Newton's laws of motion. We went through those three laws, what they mean, equations pertaining to them, some examples. We talked about the most common forces that we use in Physics 1. And today we are going to be applying those laws in some examples. So these example problems will build on each other over the next few days. I will be posting some practice assignments on Canvas today and throughout the weekend that might help you get some experience with these laws. But again, these three laws that we talked about yesterday are the foundation for all of these examples that we will be talking about over the next few days. So definitely make sure that you are familiar with Newton's three laws of motion, and we'll get into some examples of how to apply them and some situations where some interesting things can happen because of these laws of motion. All right, so to start it off really quickly, and also to just kind of jog your memory about what we talked about yesterday, I want you to think through these couple questions. Number one, is there a net force on a car driving down the highway at a constant speed? Number two, is there a net force on a baseball in flight? Number three, is there a net force on you right now? And number four, is there a net force on a car driving at a constant speed around a roundabout? So, a roundabout is one of those like weird circly intersections in the road. So take a moment, think through those questions, and then we'll come back together and talk about it in less than a minute. All right, so let's talk about it. A key thing to remember, I guess, for all of these questions is the meaning of a net force. So yesterday I was explaining a net force very quickly at the end of our class as kind of the leftover force or the unbalanced force in a scenario, right? So if we had that example of playing tug of war and your team is pulling one direction with 100 newtons of force and the other team is pulling the other direction with 60 newtons of force, which team would win and by how much? Well, your team would win by 40 newtons of force in whichever direction you're pulling. That's the net force. So when we're thinking about these forces and which direction they're acting in and how big they are, that's going to help us figure out what the net force is. So if there's some force in the scenario that's not balanced out by another force in the opposite direction that's equal in size, then there will be a net force. So is there a net force on a car driving down the highway at a constant speed? Now, we're going to imagine that driving down a highway means in a straight line. Not always, depending what part of the country you're in, but you'll find when you come to Florida that a lot of the roads are very straight. Coming from Pennsylvania, that was not the case. There's a lot of really windy roads up there. But down here in Florida, things are pretty straight. So if you're driving down the highway in a straight line at a constant speed, is there a net force acting on you? Well, no, there's not. There are forces that are acting on you, right? Gravity is still there. There's the force of the road holding you up. That's the normal force. But since you're going at a constant speed, that means that there's no acceleration, right? And so all of these forces are balanced out by another force. So the normal force pointing up is balanced by the force of gravity pulling down. Maybe the force of, the gas is balanced out by the force of friction pulling backwards. So if you're driving in a straight line at a constant speed, there's no acceleration, therefore there's no net force. Is there a net force on a baseball in flight? Yes. Okay, so we're going to assume the ideal case here, at least for my answer, we're not considering air resistance. So is there a net force on a baseball in flight? Yes, gravity is still pulling it down. And if we don't consider air resistance, I didn't specify, but if we don't consider air resistance, then there's nothing to balance out the force of gravity. So gravity is going to eventually pull it back down to the ground, and that is our unbalanced net force. Is there a net force on you right now? Well, if you're sitting still in a seat, I mean, I can't see you. I'm assuming that you're sitting somewhere, but there's probably not a net force on you if you're sitting still. Right? There's still gravity pulling down. The chair would be holding you up, and that's pretty much it. Unless you're like, I don't like jogging or something while you watch class, which again, go you. I hate running. And then the last one, is there a net force on a car driving at a constant speed around a roundabout? Well, that's the tricky part about this thing, around a roundabout. That means that your direction is constantly changing. So even though you might be driving at a constant speed, if your direction is changing, then your velocity is changing. So you do have an acceleration. And if you do have an acceleration that's not equal to 0, then you automatically have a net force that's not equal to 0. Remember Newton's second law from yesterday? Net force equals mass times acceleration. So if your acceleration is 0, your net force is 0. But if your acceleration is not 0, then your net force is not 0. Okay, so that changing direction aspect to this question means that you do have a net force. Okay, so here's another example. I want you, just like we were doing yesterday with Newton's third law, I want you to think through the interaction pair, the action force, the reaction force, and the result of this scenario. You push the gas pedal and accelerate in your car at a green light. Your car has a mass of 1,200 kilograms, and your acceleration is 4.5 meters per second squared. So again, in that first part, identify those key aspects using Newton's third law, and then use Newton's second law, net force equals mass times acceleration, to answer part B. I'll give you a minute to work through this problem, and then we'll come back together and talk about it. All right, so let's think through this question. For part A, there are a whole bunch of potential answers that you could have put down. So depending on what you identified as an interaction pair, you could have chosen um, the car pushing down on the road and the road pushing up on the car. So the road and the car would be your interaction pair. The action force would be the car pushing down on the road. The reaction force would be the road pushing back up on the car, and the result would be that the car drives on the road. It stays on the road. You could have chosen the earth pulling down on the car and the car pulling back up on the earth, gravitationally speaking. You could have chosen your foot on the gas pedal and the gas pedal back on your foot. All kinds of different possibilities that you could have chosen for part A. For part B, again, we're going to use Newton's second law here. Net force equals mass times acceleration. So the mass of our car is 1,200 kilograms. The acceleration is 4.5 meters per second squared. And so that gives us a net force of 5,400 newtons. All right, so some things to keep in mind when we're doing these example problems pertaining to Newton's laws. Objects can be moving in 2 dimensions or 3 dimensions at the same time, and Newton's second law still applies. We just have to consider each direction separately. So if we're not just talking about like a car driving on a road in a straight line, if we're talking about a car, I guess cars don't like leap off of cliffs, but like a car driving off of a cliff into water, that's not a good scenario to happen. But if that does happen, then we'll be dealing with motion in multiple directions at once, right? Horizontal and vertical. So just like we were doing with projectile motion, we have to consider those components or those directions separately. And so we still apply Newton's second law to each direction. Now we just need to specify which forces are in the x direction and which forces are in the y direction, as well as the acceleration in the x direction versus acceleration in the y direction. Now, keep in mind here that the mass of the car doesn't change. It's not like, oh, I have one mass when I'm traveling horizontally and a different mass when I'm traveling vertically. No, the mass is the same, which is why we don't have m sub x and m sub y here. But our net forces may not be the same. Our accelerations may not be the same in both directions. So we have to consider them separately. And then if we're thinking about something moving in multiple dimensions at the same time, usually we'll have to use some trig functions there. So SOHCAHTOA is the one that I refer to often as a memory device for remembering our trig function identities. All right, so here's an example. In empty space, I push a 100 kilogram satellite with 5 newtons of force at an angle of 30 degrees above the x-axis. What is the satellite's acceleration in the x and the y direction? So again, I always recommend that you start by drawing a picture if at all possible. So here is our satellite. It's 100 kilograms, that's the mass. There is our x-axis, just for reference, and our y-axis for reference. We're pushing it with 5 newtons of force at a 30-degree angle above the x-axis. Okay, so here's our picture. Well, we can see that the force is acting on an angle, so we're going to need to use those trig functions to break it down into its x component, or how far sideways we're pushing, and the y component, how far vertically we're pushing. So there we go. Our f sub x is the x component of the force, and f sub y is the y component of the force. So in the x direction, right, we have our Newton's second law. The net force in the x direction equals the mass times the acceleration in the x direction. And so remembering our trig functions, SOHCAHTOA, looking at our triangle here, here's our angle. We know the hypotenuse of our triangle is 5. We want to know the length of the side that's adjacent to the angle. So if we want the adjacent side and we have the hypotenuse, then we need to think about which trig function combines adjacent and hypotenuse. And that's CA. So CAHTOA. So we're going to use the cosine. So the hypotenuse, 5, times the cosine of our angle gives us that x component of the force. We know our mass is 100 kilograms, and we're looking for our acceleration. So when we do some plugging and chugging into our calculator, 5 times the cosine of 30 degrees, again, make sure your calculator is in degrees, not radians. So 5 times the cosine of 30 divided by 100 will give us our acceleration in the x direction of 0.043 meters per second squared. Not very fast, but it's not a big force. 5 newtons is not a big force. In the y direction, we'll do it similarly, but now we're looking for the side of the triangle that's opposite our angle. We still know the hypotenuse. Now we also know the adjacent side, if you're confident in your answer. So we could use either the sine, because that's the opposite over hypotenuse, or we could use the tangent, which is the opposite over adjacent. Now, just for the sake of this example, I ended up using the sine, because if you hadn't found the x component first, you would not be able to use the tangent in this case. So we set it up a very similar way, right? Newton's second law in the y direction. Net force in the y equals mass times acceleration in the y. So 5 times the sine of our angle equals, again, the mass is still 100 kilograms, and now we're looking for the acceleration in the y direction. So in your calculator, you would type in 5 times the sine of 30 degrees divided by 100, and that will give you a y acceleration of 0.025 meters per second squared. Again, not a very big acceleration, but not a very big force. Okay, so um, we, if you look at this example here, this picture that I drew that shows the forces that are acting on a particular object, this type of diagram that I drew is a specific kind of diagram, and they're called free body diagrams. They're also called FBDs for short, or force diagrams. So these kinds of pictures show all of the forces that are acting on an object, including their magnitudes and directions. Now, it is important that you include all of the forces that are acting on an object, even if they don't seem relevant, or even if they seem like they will be balanced out by something else, you still need to include them in your free body diagram. So usually when we draw a free body diagram, we'll represent the object as either a dot or a little box, just so you don't have to like draw a car or a person or a satellite or whatever it is that the question is asking about. So we'll just draw it as a really simple shape. And then we draw all of the forces as arrows, again, because that shows a size and a direction. And all of these arrows are going to be pointing out from the dot or the box. Okay, even if the scenario has something pushing on the box, we're still going to draw it in the same direction that it's acting, but coming out of the box. And that's just really to help us visualize which forces are acting in a positive direction and which forces are acting in a negative direction. So again, the length of the arrow shows the size of the force, and the direction of the arrow shows the direction that the force is acting. We need to label all of the arrows with the name of the force using any of those abbreviations that we went through in our most common forces table yesterday. And then again, include all of the forces in any given scenario. Don't skip any of them. So if forces are equal in size and opposite in direction, then they'll be balanced. And if all of the forces are balanced out by another force in the opposite direction, then our net force is 0. And the motion does not change. Remember, it doesn't necessarily mean that it's sitting still. It could be moving at a constant speed in a constant direction and still have a 0 net force. As long as that motion is not changing, we will not have an acceleration, and so our net force will be 0. But if there is some kind of unbalanced force, like friction or air resistance or what have you, then there will be an acceleration and there will be a net force that's not equal to 0. So, like I said, an object can be moving and have a 0 net force. It just means that the motion will not be changing. Okay, so here are a couple of examples that are similar to each other, but will give us different free body diagrams and different net forces. So the first one, the one on the left, a hockey puck sits at rest on ice. So here's our hockey puck. Now, we should be able to identify a couple of forces that are acting on this hockey puck. First of all, we're assuming that we're on Earth, and so we are always going to have the force of gravity. And the force of gravity always pulls towards the center of the Earth. So in that case, that would be straight down. Let's label it Fg, so we know that that's the force of gravity. We don't know how big it is, so the length of our arrow is kind of arbitrary at this point, since we weren't given any way to calculate it and we weren't given the magnitude in the question itself. Now, the hockey puck is not falling through the air, it's sitting on ice, so that ice is holding it up. And so we have this normal force pointed up. Again, normal means perpendicular to the surface. So if our ice is horizontally flat, then our normal force will be perpendicular to that, or straight up. Now, the length of this arrow did kind of matter. Even though we weren't given the magnitude of it in the problem or any way to calculate it, we know that this hockey puck is sitting at rest. So it's not falling through the ice, it's not being propelled into the air by the ice, which means that these two forces are balanced, right? It's sitting at rest. These forces are balanced. And so that means we need to draw the lengths of the arrows to be the same size as each other. So however long you drew your force of gravity arrow, that's how long your normal force arrow needs to be as well. So usually in a diagram, we'll represent that by like a little dash mark through those two arrows just to show that they're the same length as each other. I don't think I did that in this particular diagram. But since our net force is 0, that means that all of our forces are equal to each other in size, opposite to each other in direction. There is no acceleration happening on this hockey puck because it is sitting at rest. Net force is 0. Now, in the next case, the hockey puck is hit to the right while it's sitting on ice. And we're going to pretend that there's no friction because ice is commonly, I mean, I don't know if you've ever been ice skating, but ice is very slippery. And so the coefficient of friction is very, very low on ice. It's very close to 0. So usually when we're saying, oh, something is on ice, we're kind of implying that there's no friction, even though there might be like a smidge in reality. But usually if we say on ice, there's no friction. So again, here we have our hockey puck. We're still on Earth, so we still have the force of gravity pulling down. It's still sitting on ice, so we still have the normal force pointing up. And those two forces are still equal to each other because it's not falling through the ice and it's not being launched up by the ice. So those are equal to each other in size. Now we know this hockey puck is being hit to the right, so our applied force, Fa, is shown to the right. And there's no friction that we're considering. So there's no force opposing its motion to the right. And so there's no force pointing to the left. Now, if we were playing like street hockey or field hockey or something like that, where we're on a more rough surface where there would be friction, remember, friction always opposes the direction that something is moving. So if this hockey puck is moving to the right and there is friction, it would point back to the left. It may not be the same size as the applied force. It could be smaller if the hockey puck is going to accelerate or change its motion. Friction could be bigger than the applied force if you hit it and it doesn't actually move anywhere. So keep those things in mind for future examples. But in this case, no friction. Our free body diagram is complete. And you can see that since we do have an unbalanced force here, since our applied force does not have a force to the left that's equal in size and opposite in direction, our net force is not 0. And so there will be an acceleration. Now we don't have any way to calculate it in this example because I didn't give you any numbers to use. So just know that since the net force is 0, there will be some kind of change in this hockey puck's motion. All right, terminal velocity is a really interesting thing that can happen when we're dealing with multiple forces. So up until now, we've kind of been talking about the ideal case where we're ignoring air resistance and things are just in free fall, only considering gravity. But that's not real life. In real life, there is air resistance on Earth. And so in reality, when an object is falling, it's experiencing both gravity pulling down and air resistance pushing back up. Remember, air resistance is a kind of friction. It's friction due to air. So air resistance acts opposed to the motion. So something is falling down, air resistance points up. If you're throwing a ball up, air resistance is trying to slow it down. And so these two forces are acting in opposite directions. And at some point when an object is falling, its force of gravity pulling down will be exactly balanced by the force of air resistance pushing it back up. And so when those two forces are exactly balanced by each other, remember that means they're equal in size, opposite in direction. That means we have no more net force. And if there's no net force, then there's no acceleration. So at this particular time, then um, it stops speeding up as it falls. And it will fall at a constant speed. That constant speed that it falls at is called its terminal velocity, its ending velocity, because it will not accelerate anymore from that point, unless you're, applying another new force to it. So terminal velocity depends on the mass of the object, but more so its surface area. So if you've ever like dropped a coffee filter or like a sheet of paper on the ground, it kind of floats and falls very, very slowly. It has a large surface area. Well, let's imagine that you take that same piece of paper and crumple it up. Well, it's the same mass that it was, but now when you drop it, it falls down much faster. And that's because we decreased its surface area. So the more surface area something has, the slower its terminal velocity will be, the slower it will fall down to the ground. Of course, that also depends on what material the object is falling through. So falling through air will give you a very different result than falling through water or falling through molasses or honey or some other kind of fluid. Air is considered a fluid. So all of these things come into play when we're dealing with terminal velocity. But here are a couple of examples. So a raindrop's terminal velocity is about 9 meters per second or 20 miles per hour. A golf ball uh, has a terminal velocity of about 72 miles per hour. A person skydiving belly down, so they have more surface area if they're skydiving belly down, would be about 134 miles per hour. And if you decide you're super brave and you want to skydive head down, or even feet down, I guess, although that's much less cool, but I mean, you're still skydiving. So at that point, you're decreasing your surface area from like the length of your body to just the size of your head. So your terminal velocity increases to about 330 miles per hour, which is pretty dang fast. So we can see that the surface area really does impact um, the terminal velocity as well as the mass. Though you can see we're getting more massive as we go down that list: raindrop, golf ball, person. And so the more massive you are, the faster your terminal velocity is going to be. And I have here an interesting quote. I wrote it down. It's not in the PowerPoint, but it's a little gruesome, but I think it really gets the point across. So biologist J.B.S. Haldane wrote, "To the mouse and any smaller animal, gravity presents practically no dangers. You can drop a mouse down a 1,000-yard mine shaft, and on arriving at the bottom, it gets a slight shock and walks away. A rat would be killed, a man would be broken, and a horse would splash. For the resistance presented to movement by the air is proportional to the surface of the moving object." Right, so again, the more massive the object is, the faster its terminal velocity is going to be. And the more surface area the object has, the slower its terminal velocity will be. Okay, so when we're thinking about these scenarios that we're going to go through, some key words to look for are going to be at rest, constant speed, terminal velocity. Of course, if it says, it's accelerating or it speeds up or it changes direction, those are good things to keep in mind as well. But things like at rest, constant speed, constant direction, constant velocity, terminal velocity, all of those are going to give us a hint that the net force on this object is probably equal to 0. Okay, so keep this in mind as a key phrase to look for in upcoming examples. So here we go. If a skydiver has a mass of 80 kilograms, find the terminal velocity of the skydiver, assuming a force of air resistance of 0.32 times velocity squared. Okay. So we see that key phrase in there, terminal velocity. That's going to be one to take note of. But let's draw our free body diagram first. So here we have our skydiver. We know that the force of gravity is going to be pulling down. And yesterday I gave you an equation to calculate the force of gravity, which is mass times the acceleration due to gravity, right? That's still Newton's second law, F equals ma. Except now our acceleration is specifically due to gravity, so we use that lowercase g symbol. So our mass, 80 kilograms, times our acceleration, 9.8 meters per second squared. That gives us a force of 784 newtons. And again, that is pointed down. Since we're dealing with a terminal velocity situation, that means the force of air resistance pushing up is exactly equal to the force of gravity pulling down. So we're given this equation to calculate the force of air resistance, or the force of drag, and that's 0.32 times v squared. So if we remember that terminal velocity means net force is 0, these two forces are balanced, that's going to help us figure out what that terminal velocity, v, is going to be. So we want to know at what velocity is our acceleration equal to 0, because that's when we've reached terminal velocity. So net force equals mass times acceleration, Newton's second law. If our acceleration is 0, that means our net force is 0. So the way that we calculate net force, remember, is by adding these forces together, considering the direction that they're going. Our force of air resistance, or drag force, is pointed up, so it's positive, whereas our gravity force is pointed down, so it's negative. So when we're adding these two things together in our net force equation, we have to keep in mind their directions. Force of drag is positive, force of gravity is negative, so drag force minus gravity equals mass times acceleration, which is 0, right? Acceleration is 0. So plugging in our values for these drag forces and gravity forces gives us this, 0.32 v squared minus 784 equals 0. These two forces are equal to each other at terminal velocity. And so we can divide both sides by 0.32 and take the square root of both sides to get the velocity. Now again, your calculator may give you the positive root first, maybe not even give you the negative root for the velocity. But we're remembering that this skydiver is falling down, and so our velocity will be negative. Negative 49.5 meters per second is our terminal velocity. Woohoo! That's pretty fast. Example 4. Two blocks sit on the floor in contact with each other. That's important. Block A has a mass of 10 kilograms, and block B has a mass of 15 kilograms. You push block A with a force of 75 newtons. Now, determine all of the forces on block A. This one is kind of tricky to think through. Some of the forces are more obvious than others when we're drawing our free body diagram. Okay, so here's our scenario, right? We have the floor, and we have two blocks sitting on the floor that are in contact with each other. We are pushing on block A with a force of 75 newtons. And we're only really interested here in block A. So this is not a free body diagram. This is a picture of the scenario. Remember, a free body diagram shows all of the forces that are acting on a particular object. So since this scenario has two different objects, we would have two different free body diagrams, one for each object. Of course, we don't really care about object B a whole lot in this scenario because it's specifically asking about block A. So I'm not going to draw the free body diagram for block B. But here we have block A. Again, we know gravity is pulling down towards the center of the Earth. Since it is sitting on the floor is holding it up, so the normal force is pointing up. We have a force pushing on block A to the right, but that's not the correct way to draw a force in a free body diagram. Remember, we draw all of the forces as arrows coming out of the box. So we'll fix that in just a moment. Okay. We also have a force from block B on block A. They are touching each other. So when we're pushing on block A, it's being pushed into block B. And Newton's third law tells us that if block A is pushing on block B, then block B is pushing right back on block A with the same amount of force in the opposite direction. So we do need to include that force in our free body diagram. And that's the one that's kind of tricky. A lot of people will forget about that force. But you can see now we have these two forces that are not drawn correctly in our free body diagram. So let's fix those. Okay, so now we just took them, moved them so that they're coming out of the box. And now it's much easier, at least in my opinion, it's much easier to see which forces are acting in positive directions versus negative directions. So here is our free body diagram. So let's label these forces. Again, we have force of gravity pulling down, the normal force pushing up. The applied force to the right, we know, is 75 newtons. And then the force of block B pushing back on block A. Okay, the only value that we're given as far as forces go is that 75 newtons. However, we can calculate some of these other forces. So for the normal force and the force of gravity, remember, these two forces are going to be equal to each other in magnitude, opposite in direction, because the blocks are not falling through the floor and they're not being launched into the air. They're sitting on the floor. So these two forces are equal to each other. Well, that means that the normal force pushing up minus the force of gravity pushing down is going to be 0. Our net force is 0. There's no acceleration, no change in the motion in the y direction. We don't have an equation handy for calculating the normal force, but we do know an equation for calculating the force of gravity, and that's mass times the acceleration due to gravity. So the mass of block A is 10 kilograms. G is 9.8 meters per second squared. So that gives us a force magnitude of 98 newtons. So that means both the normal force and the force of gravity have a magnitude of 98 newtons. So we'll put that right there in our free body diagram now that we know those values. To find the force of block B on block A, we're going to again consider that this is Newton's third law and still apply Newton's second law. So in this case, that force that we're applying to move the blocks moves both of the blocks, right? If it weren't the same, like if they didn't have the same acceleration after this, then either block B would go shooting out from block A, or block B would somehow have to like let block A phase through it. And neither of those things is very realistic in this scenario. More likely, what will happen is we'll push on block A and it will move both of them at the same time. So these two blocks are going to end up with the same acceleration, which means we can kind of treat them as one object as we're analyzing its motion. So the total mass of this one big block that we're imagining would be 25 kilograms. So the net force in the x direction equals that mass times the acceleration in the x direction. So our force that we're applying, 75 newtons, equals the mass, 25, times the acceleration. And so that gives an acceleration of 3 meters per second squared. So both blocks are moving with 3 meters per second squared. Now, that doesn't actually answer our question necessarily, because that doesn't tell us the force of block B on block A. But we know that block B has a mass of 15 kilograms, and it's moving at that same acceleration, again, because it's not letting block A phase through it and it's not being propelled outward. So its force is 45 newtons. So that means block B is pushing block A with 45 newtons to the left, while block A is pushing block B with 45 newtons to the right. So we'll draw that into our free body diagram, and now we have a completed free body diagram. All right. So we finished a little bit early today. Do you guys have any questions about these examples that we went through? All right, if you do have any questions, again, feel free to type them in the chat, or hang out after I finish the recording. Feel free to ask away. But in the meantime, remember that tomorrow is our optional enrichment session about residence life and orientation at 10:30. Check out that Canvas link if you would like to attend that Zoom meeting. And then next week, we'll be doing some more examples of how to apply Newton's laws in various scenarios. So look at some of the resources on Canvas that I will be posting today. And I hope you guys have a lovely weekend. Bye.